The two main components of the R language are objects and functions. Objects are typically data structures in which you store information, and functions are the tools we use to manipulate those objects. To paraphrase John Chambers, one of the originators of the R language, everything that exists in R is an object, and everything that happens is a function. So far in your R career, you have mostly been using functions written by other people. Now you're going to learn how to write your own functions. Function writing will allow you to automate repetitive parts of your code, improve efficiency, and reduce errors. So let's go ahead and learn how to do this. Let's get started. So here is our list of learning objectives. If you like, you can pause the video and read through these, but we're going to come back to them at the end of the lesson. For now, we can start by installing and loading the necessary packages for the lesson. So go ahead and run these lines of code in order to load those packages. Let's now think about the basics of a function by learning how to create a very simple function, one that converts from pounds, which is a unit of weight used in some countries, to kilograms. So let's go ahead and do this. We're going to define a function called pounds to kg, and we'll do this by multiplying the input pounds by 0.4536, which is how you get from pounds to kg. So I'm going to do the following. I'll type function and open a pair of parentheses, and then I'll put an argument in there, pounds, okay? And then I'm going to open a pair of braces. I'll press enter. And within this pair of braces, I'm going to type the calculation I want to do, which is pounds times 0.4536. And I assign all of that to an object called kg. Finally, I will type return and open another pair of parentheses and put the object kg in there. Okay. And finally, I will assign all of this to an object which I'll call pounds to kg. And if I run this line of code, I have just defined my very first function in R. So go ahead, take a look at your environment tab of RStudio to see that this function indeed was defined. So like I said, after running this code, you'll see a new object in your environment of the type function. Now let's go ahead and see how we can use this function. So I'm going to use pounds to kg now to try to convert a value. Let's say someone who is 200 pounds. What is that in kilograms? We can see that's 90.72 kilograms approximately. Now let's go through the process of writing that function one more time to make sure you really understood it and to help you to solidify that knowledge. So we're going to slowly build up the function one more time. We start with this name function here. And then after that, we put a pair of parentheses and then also a pair of braces. Okay. And then within that function, so this thing technically is a function, but within this, we're going to put the pounds argument. And remember that pounds can be any name. We could have used X, for example, or P for pounds. But in this case, we're using the term pounds. Okay. And then within the braces is the body of the code to execute. In this case, that's going to be pounds times 0.4536. One thing to note about this body of the code is that it can extend over multiple lines. It doesn't have to be just one line. And if you are in a rush, you can also put it on the exact same line as the initial function definition, with or without these extra pair of braces. Okay, so those are just some small notes about the body. Okay, and then we need to return some key value. So here we do kg and then assign, and we can return then the object kg. Another option there would be just to directly put this inside of here, and then we don't need the intermediate object. Okay, and then one last step though is that we have to actually name the function to store it in some named object. So we type pounds to kg there, and that is how we store that function in this, let's call it a variable, okay, rather than an object, so we don't confuse objects and functions. Now we can use the function with named or with unnamed arguments, and this I think you already know. So we could type pounds to kg, pounds equals 200, or we could type pounds to kg without the pounds and type something like, let's say, 100, and we see that both of those are valid ways of calling this function. Now we can also apply this function to a vector. For example, let's define a vector here called pounds vec, and we'll just put 3 random weights, maybe 100, 200, and 300, 100, 200, and 300 pounds. And you will see that we can run our function on that vector. Now, after you have defined a function, you can explore that function's source code by typing the function's name without parentheses. So let's try an example here. If we just type pounds to kg with parentheses the way you call a function, we'll get an error because you haven't actually put in any arguments. But if you type it without any parentheses, you are trying to inspect the internals of it. And as you see, we see the actual value of that function. It is also possible to view the function in RStudio using the view command. So let's go ahead and try that. We can type view pounds to kg, making sure not to put the parentheses for the pounds to kg function. And when we run this, you get this other tab here that shows the definition of that function, nicely highlighted by RStudio. Now you can actually do this for any function in R, even those that you did not define yourself. As an example, let's view the reactable function, which comes from the reactable package, just so you can see what a function definition might look like in the wild. So here is the very scary function definition for the reactable function. As you can see, there are many tens and tens of different arguments. And if you scroll through the function, you see many if statements and many checks before you actually get to the part of the function that is doing the computations. And as you can see, it's a very scary thing. So it will take some time before you're familiar with all these different tools for writing functions. For now, we're focusing on mostly easy and intuitive functions. So go ahead now and try this practice question. We want you to create a simple function called years to months that will transform a given age in years to the equivalent age in months by simply multiplying that age times 12, or that number times 12. Okay, so try it out with the with this construction here, years to months 12. Make sure that gives you the correct value. So go ahead, pause the video, and try that out. So now let's go ahead and write a very slightly more complex function in order to give you additional practice in function writing. Our function is going to try to convert Fahrenheit, a temperature scale, to Celsius, another temperature scale. So here's the formula. The Celsius is equal to 5/9 times the Fahrenheit value minus 32. Let's see how we're going to write that. Okay, we're going to test it with this construction here, Fahrenheit to Celsius 32, which should give us the value of 0. So we start by typing function, and we're going to convert Fahrenheit to Celsius. So we take in an input of Fahrenheit. Okay, then we open our braces, and then within that, we're going to say that the Celsius value, Celsius, is equal to 5/9 times the Fahrenheit value there. I'll just copy that or click on that, minus 32. All right. And instead of the equals to here, we really should use the back assignment operator. Sorry about that. And now we return the Celsius value. Okay. Our final step is to name this function. So Fahrenheit to Celsius is going to be its name. Let's go ahead and define that. And now let's run this line to test it. And as we can see, Fahrenheit to Celsius of 32 does give us 0, which means the function is working as expected. Now let's try and test out this function on a dataset, a built-in dataset in R called air quality. So let's see how we can use Fahrenheit to Celsius on air quality. So the air quality data frame has a column called temp here, although it's abbreviated. This fourth column is called temp. We can first select it. So we pipe into the select function and select the variable called temp. Okay, and we can run this just to see only the temperature. And then we're going to apply our function, Fahrenheit to Celsius, to that temp column, which at the moment is in Fahrenheit, as you can see by these very high numbers for the air temperature. So we say mutate, and we can say maybe temp, Fahrenheit, hopefully I spelled that correctly, is equal to We copy our function definition here, Fahrenheit to Celsius. Okay. Sorry, this should be temp Celsius, not temp Fahrenheit. My bad. Of this temp column there. All right. And we can delete these comments because the code is clear enough. So let's run this. And as you can see, you have now the equivalent temperature in Fahrenheit in Celsius. So now that you've seen a few different examples of functions, let's think of when you should write a function in the first place. We'll look at some principles for this. One key principle is reusability. Generally, it makes sense to write a function to avoid repetitive code. If you have a calculation or a manipulation that you do very frequently, it'll make your code much simpler and much more efficient, probably, to nest that into a function. Another reason to write functions is to enhance the readability of your code. So especially when you give your functions descriptive names, it can really help to enhance how easy it is to read and understand what is going on in the code. This is not so obvious with the kind of simple functions that we're doing. For example, the Fahrenheit to Celsius function. You can see that these two lines of code are of sort of similar levels of complexity. Although this one is a bit easier to understand what's going on. It's obvious that this is Fahrenheit to Celsius. Whereas here, if the person doesn't know what this formula means, they may be a bit confused. But this effect will be much more apparent when you write more complex functions, where if you don't nest into functions, your code will be very, very hard to parse. Another reason to write functions is to enable sharing of your code. So if you write a function, it makes it easy to share that code with others, either through packages, which we'll talk about later, or through just simple scripts. Now here is a small side note on the utility of functions. So generally, amongst the most useful functions you're going to be playing with will be data frame and plotting functions. So for example, here's a function that I use often, which creates an epidemic curve from a dataset. So it's going to take in a specific data set and a date column. That's the dates when the disease was diagnosed amongst the population. And it will just simply plot an epidemic curve based on that. So if we take this outbreaks Ebola Sierra Leone 2014 data set, which has this date of sample date column, we can simply run this function, which I define up here, and it'll give us immediately an epidemic curve. And this is something that I use often. However, data frame and plotting functions are a bit more complicated, as you can see from some of the weird syntactic elements here. So in this specific lesson, we're mostly just going to focus on simple vector functions. Okay, so we'll focus on vector manipulation functions to give you a solid foundation in function writing. And then in a future lesson, we'll look at how to do these more complex data frame and plotting functions. Now here's another practice question for you. You're going to do the opposite of the Fahrenheit to Celsius function and instead write a Celsius to Fahrenheit function to convert any Celsius temperature to the equivalent Fahrenheit temperature using the formula given here. Okay, and when you're done with that, go ahead and test that out on this temperature column in the built-in Beaver1 dataset. So pause the video and try this out. Next, let's think about functions with multiple arguments. So functions typically will have multiple arguments, and we're going to look at a case where a function has 3 arguments. Specifically, we're going to write a function called calculate calories that will deduce the number of calories when given specific grams of macronutrients. So let's go ahead and write this function. Make sure you're typing along with me. So we'll write function, okay, and maybe we can already define the name, calculate calories. Define that as a function with 3 arguments, so carb grams, protein grams, and also fat grams. Okay, we can delete that comment. And what we want is we're going to output some result. Let's call it result. Maybe I'll put this on a new line. Whoops. Put this on a new line so it's easier to read. So our result is going to be the number of carb grams times the number of calories in a gram of carbs, which we're going to approximate as just 4. Okay, and we can put this in parentheses just to make it a bit easier to read, plus protein grams, which also has just 4 calories per gram, approximately, plus fat grams, which will put as having 9 grams or 9 calories per gram. Okay. All right, and we put that again in parentheses. It's not actually necessary in this case, but it will help us think about the function. And then we return now this result, this added result. So I can get rid of this set of comments, remove that S from there, and I'm going to press Control Enter and define that function. And now let's test the function with these arguments and see if it comes out nicely. And it seems to have worked well. Now, one potential issue with this function is that if you don't supply all of the arguments, the function will give you an error. Let's see what we mean by that. Let's try calculating calories of 50 grams of carbs and 25 grams of protein without an equivalent fat grams argument. So if we run this now, you can see it says argument fat grams is missing with no default. So what we're going to have to do, therefore, is set what's called a default value for that specific argument, in this case, fat grams. Let's see how we can do this. So we're going to change here. We take our same function from before, and we're just going to change fat grams here to equals to 0. Okay. What that means is if fat grams is not supplied, then it'll just be 0 times 9, and we'll still be able to get a result. So let's try that now with 50, 25, which are position matched to carb grams and protein grams. And we run that, and now we get a value of 300. So now it works. However, of course, it would make sense for all of the different arguments to have optional default values, okay? Or to make the argument optional by using default values. Let's go ahead and do that. So we add now carb grams equals 0, and protein grams also equals 0, all right? And let's now define that function, okay? And now we can call the function with no arguments, or maybe with some arguments. So let's try with no arguments. What do you think is going to happen if we run this function with no arguments? Okay, so we get the value of 0, which kind of makes sense. With 0 grams of carbs, 0 protein, 0 fat, you have 0 calories. And we can use 2 arguments, or 1 argument, and so on and so forth. Now, on the topic of functions with multiple arguments, here's a practice question for you. You're going to create a function called calcBMI that will take in the weight and also the height and output the BMI of that specific individual or of that vector of values. Okay. When you're done with that, try to apply that function in the following way on the medical data smart pill dataset, which has a weight and a height column within it, which are already in kilograms and in meters or cm. So you may actually need to do some manipulations there to get that to work. So go ahead, pause the video and try that. Now, when thinking about functions and passing things to internal functions and so on, it is useful to understand what is called scope in R. So scope refers to the visibility of the variables and objects within different parts of your code. And that is a vague definition, so we need to actually think about some examples. Consider that some objects are going to have local scope, okay, and will not be accessible outside the function. Specifically, objects that are defined within the function will have what we call local scope and are not accessible outside the function. Something that's accessible globally or outside the function has what we call global scope. That's probably still vague. So let's consider an actual example. So imagine that we wrote the pounds to kg function in the following way. Okay? Pounds to kg function, it takes in the pounds argument, it multiplies it by 0.4536, and it outputs 2 kg. Okay? Now, a naive R user who doesn't yet know how functions work may be tempted to access this kg variable outside of the function. So they may think, okay, I've defined this function and it does this manipulation, creates an object called kg. So when they run this, they may expect that if they type kg now, it will have the value of this, of 50 times 0.4536. But as you can see, you get an error, object kg not found, even though we've run this function, which in theory is defining an object called kg. So hopefully you see the issue there. To use a value generated within a function, we must return that value from the function, which is what we've been doing so far. So we supply it to kg, and then the return argument is important there to actually pull that value out of the function, okay, when we call it. And then we store that function's result in a global variable. So instead of just doing this here, typically what you do then is you do all of that assigned to a kg variable, which is what we've been doing, but here we just want to make it explicit. And now we can call kg and it contains the value which we... When writing functions, it's going to be crucial to understand conditionals. The conditionals if, else if, and else help to control the flow of code execution in R, and they're especially useful in functions. So R implements these conditionals, like I said, using three main things: if, else, and else if. By now, I think you've probably seen these in your R career, okay, but we'll dig into them in a bit more detail here. So if is used to run code only if a specific condition is true. So here is the structure of an if statement. Okay, so we type the word if, and then typically we put a space. After the space, we open up our parentheses, and you type something that's going to be a condition. For now, we just put the placeholder condition, and then we have our braces, and within the braces, we're going to have some code we want to run. Okay, so basically, this thing will be evaluated as follows. Let me delete this. If something here evaluates to true, then the thing in here will run, and if not, it won't run. Let's look at a more practical or real example. So we're going to try to convert from Celsius to Fahrenheit using this if condition. Specifically, what we do is we define a value called Celsius to be 20, and we define this other object here, convert to be Fahrenheit, and we're going to write the following if condition. If converts to is Fahrenheit, then we create the Fahrenheit object as this multiplication here. So let's try that. We write if, okay, and our condition is that the converts to argument is equal to Fahrenheit, and if all of that is true, then we want to do the following: create a Fahrenheit object as the Celsius object times 9/5 and then plus 32. Okay, so let's now go ahead and run that. So we define Celsius, define convert to, and all of this code will get run out once when I press Control Enter here. So if we run all of that, so what this means now is we've created a Fahrenheit object within that. It may be useful to print that object, so let's go ahead and print it, Fahrenheit. So let's run that one more time, and now we print the equivalent of 20 degrees Celsius in Fahrenheit of 68 there. Okay, hopefully you're getting the hang of it. So if convert to is Fahrenheit, the code body is executed, and if not, that code body will be skipped. So let's see what happens when this is not actually Fahrenheit. So let's just call it not Fahrenheit, or let's call it blah blah, blah blah. All right, and now if we run this, you'll see that nothing happens. All right, because this if clause here gets evaluated to false, and therefore nothing happens. So what we might want to do then is add an else clause that will handle the case where this thing is not true. So where convert to is not Fahrenheit. So let's see how to use else. So again, we have convert to now is equal to Kelvin. We're going to copy this whole thing, and we're going to try to add an else clause there. Okay. So if convert to is Fahrenheit, do that. Else, just put a space and you type else. Some of these spaces aren't actually necessary for the code to run. As you know, R is mostly code space agnostic, but it helps for readability. Okay. So else now, what do we want to do? Let's, for example, just print the original Celsius value. Okay, so we're just going to print the original Celsius value. And maybe we can copy the Celsius definition here, just so it's super clear everything that's happening in this code chunk. All right, so make sure you pause the video and try to understand exactly what's going on here. If convert to is Fahrenheit, we want to run all of this code. Otherwise, we're going to run this code. So let's see what happens now that convert to is Kelvin. Let's try running all of that. Take a guess as to what's going to happen. We print, of course, the original Celsius. If we change the value of convert to Fahrenheit, now we print the equivalent Fahrenheit temperature. Now the final conditional construction is else if, and we use that to check multiple conditions. So if and else is just one single branch. If this, do X, otherwise go Y, but else if will let us take many branches. So if this go this way, otherwise go this way, and otherwise go that way, and otherwise go, and so on and so forth, in a set of nested conditions like that. So let's see how to use else if. So we're going to take our existing code here, And I'll just get rid of this. All right. And we'll manually type in our else if there. So we're going to type else if, okay, and then we open parentheses for our condition. Convert to is Kelvin. If that is the case, then we want to define an object called Kelvin, we can say, and that will be Celsius plus 3, what's the value? 273.15. Okay, and we can also print that for now. So print that Kelvin value. Okay, and we put a space there. So this is how you can check these two different conditions, and if both of those conditions fail, then you fall back on this last else. So let's try this now with convert to set to Kelvin, and our Celsius value is still set to 20. So if we run this, we can see that we print the equivalent Kelvin value. And so like I mentioned, this code is handling 3 different scenarios. Either converts to is Fahrenheit, or convert to is Kelvin, or neither of those is the case. And in that case, you just keep the original Celsius value. Okay. Now it's important to note that you can have as many else if statements as you need, but you can only have one else statement. So if you had other conversions you wanted to do here, maybe else if convert to was centigrade or something like that, you could just copy this and add another else if there and keep going on and on. But you can only have one else. Else is the final thing. Okay, else is if none of the previous conditions was fulfilled. Okay. So finally, let's try to encapsulate all of this into an actual useful function. So I'm going to copy all of this now, and we'll put it here inside of our function definition. All right, and we're going to have to rewrite this a little bit. So if our convert to is Fahrenheit, let's create an object called out. Okay, that's what we're going to send out of the function, and we define it as Celsius times that. And same thing, if convert to is Kelvin, we also create an object called out, and we don't need to print since we're going to return it. And otherwise, we will just return the out. So let's say we'll say out is the Celsius value. Okay, so make sure you pause and understand what's going on. And hopefully, if you're following along, you know we're still missing one key thing, and that is to return this out value. Okay, so if convert to is Fahrenheit, we'll go down this path, but we won't go down those two. We will have defined out though, and so we can return it. If convert to is Kelvin, only this path will be evaluated, and so we'll have our out value being the Kelvin, and otherwise our out value will be the Celsius. So let's go ahead and define that function. We can see that it's defined successfully, and we can test it. So Celsius converts. Let's try to convert 20 degrees Celsius to Fahrenheit. You can see that's 68 Fahrenheit. That seems correct to me. And how about to Kelvin? That's 293.15 Kelvin. That is also indeed correct. Okay. Now there's one problem here though with this function, and that is the problem of silent failure. So if you pass an invalid value for convert to, the function will fail without any informative error message. So if here you type something like Celsius, okay, or full, or blah blah, and let me just delete this so you can see that it's actually coming out that way. It just gives you 20. So it gives you the original value without telling you anything about what you did wrong. And this can be confusing because someone may not realize that they made a mistake in their code. So what we need is to have something called error handling. We need to add some error handling to the function. Okay? But before we get to error handling, try this practice question to get the basics of conditional logic. So we're going to, here you're creating a function named check negatives, and it'll analyze a vector of numbers and print whether there's any negative number in that vector. So here it uses the any function here. If any of those vectors, any of those numbers is less than 0, it prints there's negative numbers. Otherwise, it prints no negative numbers. Now, an important thing about this function, though, is that it is not going to run if you try to define it, because there's a bunch of syntax errors. So your task is to read through the function and understanding the syntax for conditionals that we've defined above there, try to fix the issues with the function. So pause the video and try that out. So now let's think about how you can use conditionals to check different arguments, as we said would be important for our function. So argument checking is crucial in our functions to ensure that the inputs are sensible. Okay, and without any checks, you may return incorrect results. You may fail silently, as we had in our Celsius conversion function there, or you may fail with an uninformative error message. So you get an error, but the person, the reader, the user doesn't know what to do with that error. So let's see what we can do to fix this. So let's look at an example using the Celsius convert function, okay, which we have seen that is problematic because if we put any random string in here, it just returns the original value without any informative error message. So let's look at the definition of that function and see how we can fix it, all right? The problem, like I mentioned, is that it fails silently when convert_to is not a valid temperature scale. So what we're going to do is we're going to use the stop function to stop the execution of Celsius convert and return an error message if this convert_to is not a valid temperature scale, all right? So we're going to validate the convert_to argument. First, we'll write out the validation without the function, and then later we'll integrate it into the function. So let's see how we do this. So first we define convert_to to some random scale. We can just call it blah blah. All right, and we define that. And now let's try to write this if statement using the stop function. Before I do that, let me just show you what the stop function does. Stop. If you put any string in here, like bad person, and you run this, it'll say error bad person. So it's just a way of erroring with a message. So let's see how we can integrate that into an if conditional. So we say if, and then convert_to is not in Fahrenheit or Kelvin, not Celsius, rather, just Fahrenheit or Kelvin. Convert_to in C of Fahrenheit or Kelvin. Whoops, Kelvin. And we want to take the negative of this. So if it's not in that vector there, okay, then we want to stop and give an error like maybe convert_to must be 1 of Fahrenheit or Kelvin. So now if we run this conditional here, you can see it gives us the error that convert_to must be 1 of Fahrenheit or Kelvin, okay? And maybe we can put these in quotes just so that it's super clear for the user, okay? And if we set this now to one of the valid scales, like let's say Fahrenheit, and we run this, okay, you see that the stop message is not shown. So now this will stop us only in a case where the value of convert_to is not a valid scale for our Celsius convert function. Okay, let's go ahead and see how we can actually integrate this conditional now into the function. So we're going to copy the function from where we defined it previously, Celsius convert. Copy all of this, okay, and let's try to add this checker to it. So we're going to just copy this here. And if convert_to is not either Fahrenheit or Kelvin, we throw a stop function, all right? And we could define the function like this. However, we should notice that there's no longer a need for this else statement because stop will halt the execution if convert_to is not valid. So this else statement normally catches cases where convert_to is neither Fahrenheit nor Kelvin. However, our stop function here will catch all such cases where convert_to is neither Fahrenheit nor Kelvin and throw an error message. So we no longer need this else command there. One thing you could do instead of what we have above is put that stop at the end of the else. So this stop here could actually go in the else. But it is often better to put your checks, your argument checks, at the start of the function because it's easier for people to read and it's easier to make sense of. So here we check that convert_to is valid. And then based on whether it's Fahrenheit or Kelvin, we deploy one of these lines of code. And another thing we may do here is add some comments. Here we can say checking validity. And here we can say converting value. Okay, just so it's easy to make sense of the function. Now we can define this new function, this upgraded function. And like I said, no longer a need for the else statement. So let's go ahead and try it on, let's say, centigrade. So if we try this now on centigrade, you can see it gives us an error. But if we set it to one of the valid options like Fahrenheit, now we get the actual correct value. Now a pro tip on arguments checking. Usually there are many different things you could check for in terms of the validity of a function. Okay, so you end up needing a balance in terms of ensuring that your function is not too complicated looking, and also that it is not too slow running, because each check takes some compute energy or some compute time. Okay, over time, though, you will develop a good sense of the right amount of checking. Okay, mostly by looking at other people's function definitions. In this case, we just have one check. This is probably not enough. You may need one or two other things to check. Maybe you may want to check that the Celsius value is actually numeric, and maybe one or two other things like that. But over time, you'll get a sense of what is necessary to check and what not. For now, I would say it is usually a good idea to err on the side of more checking, especially if it's a function you are writing for yourself. Now here is some argument checking practice for you. So I want you to consider the calculate calories function that we wrote before. What I'd like you to do is create a copy of that called calculate calories 2 that is going to check that carb grams, protein grams, and fat grams are all numeric. You can use the is.numeric checker for that. And if not, you need to print a stop function with a useful help or a useful error message. So go ahead, pause the video, and try that out. Now, a final topic on conditionals within functions. An important realization, and also an important source of errors that you will find, is that if statements are not vectorized, and therefore they only evaluate the first element of a vector. This is something that if you are not told, you will realize it usually in the course of running into an error in your code. So let's make sure we understand this fact about if statements. Okay. So consider this attempt. We're going to try to create a function called classifyTemp that will classify temperature readings based on if they're below 35, between 35 and 37, or above 35, with those categories corresponding to hypothermia, normal, and fever, respectively. These are human body temperatures, as you can imagine. So let's try to define this function. And make sure you pause the video and try to understand what each of these if conditions is doing. It should be intuitive to you after our foray into conditionals. But there's a big problem with this function. And that is that it's going to work for a single value. So here we try to classify 36, which we know is normal. Okay. But if we try to convert multiple values, like a vector here, of temperatures, which should normally work in R, we'll get an error. It says error in if temp less than 35, which is our first conditional up there. The condition has length greater than 1. So as you can see, if statements do not work on conditions that are greater than 1. What that means is the following. It means that when you're trying to write a conditional statement in a function that's supposed to operate on a vector, you need to use something else, the if, else, or case when functions, for example. Okay. Recall that when we were using the if statements before on the Celsius convert function, we only had one value in those ifs. That's the convert to and convert from. You don't supply a vector of values for the convert to and from. It's just one value it takes at a time. So there the if statements made sense. But here, an if that is on the temperature vector here, which you would imagine would come in as many different values, is not going to work. Okay, so we're going to use if, else, or dplyr case when. And these are functions I think you're familiar with. So let's try to write now classify temp. Instead of as this thing here, we'll try to write it as a series of if, else statements. I'll copy this here just so I can get the actual conditionals. And make sure you're typing, make sure you're typing along with me, all right? So we're going to write a function that is going to take in a temperature. And we open up our braces there. And we're going to say if else, which is a vectorized version of if, that takes in 3 arguments, the test or the conditional, the yes and the no. Yes is what happens when the if is true. No is what happens when it's false. So if temp is less than 35, okay, what value do we want to return? We want to return hypothermia. Okay, hypothermia. Okay, and we're going to define this to be, let's call this our out. So if else temp is less than 35, we want to print hypothermia. Okay, and otherwise, what do we want to do? We want to evaluate the next if else. So otherwise, if else, okay, temperature is in this range here. Okay. Then we want to print out normal. And otherwise, we want to put something in here. But what is this value we want to put in there? Is another if else. Okay. If else, our last if else, temperature is greater than 37. Then we want to put what? We want to return fever. Fever. And otherwise, what do we want to return? Probably just return invalid or NA. Okay. Because if it's not in any of these ranges, either below 35, between 35 and 37, or 37, then it's something weird and random that that is problematic. Okay, so now we can return this out value, return out. Now this is your first example maybe of seeing nested if-elses, and I'll tell you that they are not so good to write. That is, generally you shouldn't write such code. So I'm going to show you the alternative in a second, but just to give you the idea, as a direct alternative to if. So now we can run down this classify temp, and we'll see that it will run on the temp vector. Okay, remember that temp vec was 36, 37, 38. Only one of these is fever, and we get that third one there being fever. And this therefore would also work on a data frame. Now as an alternative to these nested if-elses, dplyr has the wonderful case when, and we can use this as an alternative here. So here we have classify temp case when temperature is less than 35, hypothermia, and so on and so forth. And in the case where it's not in any of those conditions, you return NA character, and we output this to an out variable, okay, and we return that out object or variable, as you prefer. And now we can run this updated function on our temp vec, and if we run this, we get the output of normal fever, which is just as it should be. Now, because this function works with vectors, we can also use it with columns of data frames, which are actually just vectors. So let's try it with this dataset from the NHSR datasets package. I'll just highlight this and run just that so you can see the you can see the dataset, although R Markdown refuses to print the full names there. So you have to look at that on your own time on your console. There is, however, a temperature variable called just temp. And this gives the temperatures in degrees Celsius. So we can try to mutate and create a new variable called temp classif, or a new column, which stands for classification. And that's equal to our classify temp function acting on the temp variable. And if we run this, we see that it classifies them successfully as normal, fever, or in some cases, hypothermia. Now here is a practice question for you. So consider the following attempt at writing a function that calculates dosages of the following tuberculosis drug for adults weighing more than 30 kg. Okay, so it's a function that first has a stop clause for if the weight is less than 30, and then otherwise, depending on the specific weight class, it returns specific dosages in milligrams, I believe, of this drug. Okay. However, as you notice, it uses if statements, if conditionals, on something that should be a vector, or a vector with many elements. So this function is not going to work. And so your task is to write a new function that can handle vector inputs with multiple values, okay? And to implement this check they did here, where if weight is less than 30, you're going to have to use if any of the values of weight are less than 30, okay? So here we've helped you with that function check. So pause the video and try this out. So you've now made it to the end of the lesson. Let's look at our list of learning objectives and make sure you actually feel like you've mastered these. If not, you may need to rewatch the video or consult external resources. Hopefully by now you feel like you can create and use your own functions, very simple functions, but hopefully you feel like you have the basics. By now you should be able to design function arguments and set default values for those function arguments. You should be able to use conditional logic within your functions, the if, the else if, and the else commands. Okay, you should be able to check and validate function arguments to prevent silent failures or uninformative errors. Okay, you should know what function scope is and how to manage that scope, and you should understand local versus global variables. You should be able to handle vectorized data in functions, especially in the context of conditionals. And finally, you should know how you can store your functions for easy reuse. So congratulations on getting through this lesson. You now have the basic building blocks to create your own custom functions in order to automate repetitive workflows. Of course, we've just scratched the surface, as we often do in these videos, of the topic. So you're going to keep learning about functions as you go through your R career by looking mostly at other people's functions and getting intuitions about what makes a good function, what makes a bad function, and different tools to use within those functions. Hopefully, though, you feel like you now have a good foundation to build on. For now, I'll be signing off, and I'll see you in the next video. Bye-bye.